All right. Hello, everyone. Happy Wednesday. As I mentioned in Monday's class, right, we have a quiz this week. Same as, I guess, our typical quizzes, our quiz 1 and our quiz 2 and whatnot. Except for, right, we have enough topics for this quiz already. So the 14.6 stuff that we talked about in Monday's class will not be present on the quiz tomorrow. However, it will be present on the next quiz, just because that quiz will only have 2 subjects otherwise. So adding this third one doesn't seem so bad, especially because our quiz 3 here, I think, already has like 5 or 6 subjects or something like this. We don't need any more subjects on this quiz. So anyway, that's just a reminder. All of this is written in D2L, the announcements, and on the in the quizzes tab and whatnot. So if you want to see explicitly what topics are on the quiz, by all means, you can take a look there. I think that's my only administrative stuff. Any questions before we get into the math? All right, math it is. So in today's class, we're going to be talking about another use of partial derivatives, and we're playing this old Calculus 1 game that you used to play with derivatives in order to find mins and maxes. And so in the pre-class video, we go through kind of a bit of the stuff that I want you to recall from your Calculus 1 class about local mins, local maxes, absolute mins, absolute maxes, those sorts of things. And then I need to go into, well, we're going to build up to how do we do this in a multivariable case. So I first need to tell you about critical points, right? Critical points back in Calculus 1 were just where the derivative was either 0 or undefined. And those things were nice because they were your potential mins and maxes. So if you found your critical points, you kind of knew all the potential places where mins and maxes could be. So in Calculus 3 here, it turns out they have to be a little bit more careful. So it's where either both of your partial derivatives are equal to 0, or if either one of them is undefined, it turns out you could have a critical point there. So again, we're kind of gathering up all the places that could potentially have mins or maxes. So largely in our class, though, I mean, we're going to be taking a couple partial derivatives and figuring out what it takes in order to make both of these things equal to 0. Where one of these partial derivatives doesn't exist, doesn't really come up so much in our class, but again, for very complicated functions that would be hard to do by hand, technically, if you want to get the complete set of where you could have critical points and whatnot, you do need to include where partial derivatives don't exist. And just as kind of an FYI, a reminder for the absolute value of x, right, at 0 here, when you have this jagged turn, right, this is a place where the derivative doesn't exist. So when you make these very quick changes, like this is an example of a derivative not existing. All right, and then finally, critical points that are not local extrema are called saddle points. So we now have a name for these things. In Calculus 1, this would be like x cubed. You could find at 0, we do have a critical point, and yet it's not a min or a max, right? Kind of around it, you can still get bigger values and smaller values. And so that's going to be called a saddle point. And then we kind of go into that, it would be difficult to create a first derivative test in a multivariable situation. Not impossible, but complicated for sure. But it turns out the second derivative test ends up much nicer as far as classifying, is this critical point a min or a max, or what is it? Maybe it's just a boring critical point, aka a saddle point, right? And so I talked through in the pre-class videos kind of the pain of the first derivative, right? If you wanted to try to recreate a first derivative test, why that's difficult. And then I go into, well, we want to use then a second derivative test in order to figure out and classify our mins and maxes. So that's what I'd like to start with for the in-class stuff. So this has been a quick review of the pre-class video. Any questions from any of this before we jump into the new stuff? All right. Well then, why don't we go ahead and switch gears here. So this is going to be our second derivative test. We do need that in order for this to work out, you do have to have the case where your critical points are given by 0 for your partial derivatives, right? You can't have one of these situations where they're undefined, otherwise this test doesn't work. And then this D value that I'd like to define here is going to be the determinant of the Hessian matrix. So the Hessian matrix looks like this. And it takes all of your second order partial derivatives. So first a derivative with respect to x 2 times, then with respect to x once, and then y once, and then y once, x once, and then both y's. Of course, we could calculate this out, right? The determinant looks like this. We have f sub xx times f sub yy. That's the first diagonal. And then we subtract away our second diagonal. And you may recall from 14.3 that if you have relatively nice functions, and so these are continuous, so they satisfy that they're relatively nice, that mixed partials, that is, if you do x first and then y, versus if you do y first and then x, right, that they give you the same thing. That was Clairaut's theorem. And so you are allowed to switch your order of derivatives. And so these two right here, the f sub xy versus the f sub yx, it doesn't matter in which order you take those derivatives. And so that's why we could just say, well, it's f sub xy and square that. All right, so that's what I mean, that you need to consider all of your second order partial derivatives, right? So this thing includes all of them here. And then here comes the test. So the test goes like this. If you have this D value that we're going to evaluate at our critical point, because after all, we're interested in classifying our critical point. If this is positive, so you can see that's in cases 1 and 2, it mentions that this D value is positive. What I would like you to think about is that we are in Calc 1 world. So in Calc 1 world, we're going to go back and use our regular old second derivative test in this case. And for the second derivative test in Calculus 1, it said if our second derivative was less than 0, that meant something about concavity, right? It meant that it was concave down. So if you have a critical point, but then it's being concave down, it's being stretched downward, that means that your critical point must be a maximum. So f has a maximum, or a local maximum, at our critical point, AB. And likewise, in the second case here, still in Calc 1 world, but if your second derivative is positive, that means it's concave up, right? Concave up means that there's going to be a local minimum. At your critical point. And then finally, if your D, this determinant of our Hessian matrix, is less than 0, then we're going to be in Calc 3 world. And the new thing here in Calc 3 world is that we have saddle points. Before those, we didn't define a saddle point. So then F has a saddle point at our critical point there, AB. So that's the new bit. And then lastly, just like in Calculus 1, the second derivative test has this annoying thing that it doesn't know everything, that there can be sufficiently complicated functions out there that it doesn't know if they have minimums or maximums. And that happens when this D is 0. So if this determinant is 0, then the test is inconclusive. That just means that the functions, again, the second derivative test here can't classify that critical point for that function, and that you would need to use some other test, which largely means it's going to get more complicated and probably is hard for humans to do by hand. So probably would not be appropriate, right, for a timed quiz or exam or something like this. All right. So, any questions about this theorem? Yeah.
Why the determinant, like who came up with like the determinant being this, like why?
Well, it was Ludwig Hesse, of course. So yeah, some German mathematician. His last name, Hesse, is the Hessian part of this matrix. And yeah, what you need to do in order to actually prove that this is the right thing to do, because it's fairly complicated, right? You wouldn't maybe guess that this would be the way that you combine these things. It at least doesn't seem intuitive. And it turns out what you need to do is, well, we've been talking about a little bit tangent planes, right? And tangent planes are great for linearizations and all that sort of stuff, but they don't really tell you about the curvature, right? For mins and maxes and stuff like this, you have to kind of have some curvature to your surface. Otherwise, if it's just a straight plane, you're not going to have a min or a max, right? It's just going to go on forever and it's going to keep on getting bigger and bigger. Or if you go the other way, it's going to keep on getting smaller and smaller. So you need that curvature. And so instead of a tangent plane, you have to talk about kind of some tangent quadratic surface, right? And in order to do that, just like in calculus 2, we had these things Taylor polynomials, right? And a first degree Taylor polynomial gave you the tangent line. But if you got a second degree Taylor polynomial, this would be like the tangent parabola or something like this. Well, you need to develop all that in 3 dimensions, right? So you need to have that with x's and y's. So you have these polynomials. And if you do the this kind of tangent quadratic surface approximation, then the coefficients kind of drop out very nicely. And you can kind of see why this is the right way to combine these things. And then you say, oh, well, actually, this could be embedded in a matrix, right? And so you could do this, and it kind of seems semi-natural that way, right? That where does this quantity come from? So once upon a time, I had a nice proof of this that I thought was fairly readable, which is sometimes not always the case for mathematical proofs. So I'll try to dig that up, and maybe I can post it on D2L under my folder for anyone who's interested about, how would you go about proving this? But forewarned, it is complicated. So. All right. Well, why don't we try a problem then? See how we're actually going to utilize this stuff. In 12.6, right, we had this thing, the hyperbolic paraboloid. And I said that, it looks like a saddle or a Pringles chip, right? And I claimed that there was a saddle point there. And so I'd like to be able to prove that now with our information that we have. So the first thing is, you can almost break these up into 2 steps, right? There's a bit where you need to find all of your critical points. And then there's a second bit where you need to classify them, right? So the first step is finding the critical points. And then the second step is, okay, well, what are they, right? Are they mins? Are they maxes? Hopefully it's a saddle point because that's kind of the premise of this problem. So let's go ahead and first find these things. In order to find them, we need to take some partial derivatives. And remember, we're looking for when our partial derivatives are either both 0 or one of them is undefined. So, okay, here's my function over here. If I take an x derivative, I get negative 2x. And if I take a y derivative, I get positive 2y. Are there any xy combinations that I could plug into this that would make these undefined? Is there any real number that you could plug into these things and make it undefined? Not so much, right? In order to make it undefined, we're looking for situations where we're dividing by 0, or putting a negative into a square root, or maybe a negative or 0 into natural logs, right? But I mean, these ones are just nice, easy polynomials. No matter what we choose for x and y, they're always going to be defined. And so our only hope for critical points is if we can make both of them equal to 0. So if I want my first one to be equal to 0, this is going to require that the x coordinate must be 0. If I would like my second partial derivative with respect to y to be 0, this is going to require that my y coordinate must be 0. So if I need both of these things to be true, right, there's an and joining these statements, then that means that my only critical point is going to be at 0, 0. So this is my only critical point, and there are no others. So now step A is done, right? And now I'd like to move on to step B. Now that I've found all my critical points, I would like to classify them. In order to classify them, that's where we're going to be using this new theorem right here. And we need to calculate out this determinant of our Hessian matrix, which means that we need a lot of pieces when it comes to second derivatives. So let's go ahead and calculate out some of these. So f sub xx, f sub xy, f sub yy. I've already made it part of the way there, right? I have my partial derivative with respect to x up here. So I can take another derivative with respect to x, and that's going to give me negative 2. I could instead take a derivative with respect to y of that negative 2x, and that's constant with respect to y, right? There are no y's. And so that derivative would be 0. And then finally, if I look at my second one here, my first derivative with respect to y, and I take another derivative with respect to y, then I'm going to get just 2, or 2 times 1. So this means that my d value here is going to be equal to -2 times 2 minus 0 squared. You can also, I mean, if you want to put it in a matrix and all that sort of stuff, you certainly can, right? But again, you need to do your f sub xx times f sub yy minus f sub xy squared. That's this bit right here. This quantity is equal to -4. And if I was showing work on a quiz or an exam or something like this, remember the main thing that we're interested in is this number positive, negative, or 0? So I'm just going to include in here that -4 is less than 0. That's the thing that I care about. And so therefore we are in calculus 3 world, which means we have a saddle point. So 0, 0 is a saddle point. And so this is how you mathematically prove that this hyperbolic paraboloid has a saddle point at 0, 0. Questions? This first one here was admittedly on the easier side. We're still warming up. They do get harder. Yes. What is a saddle point? Yeah, so a saddle point is, I like to start off again kind of in calculus 1 mode for the time being, right? So if I have a minimum, that would be like there on a parabola sort of deal. Or if I have a maximum, maybe a parabola is, flipped over. And again, these could be more complicated things. They don't have to be just parabolas. They could be something like this. And then you could talk about local maximums rather than absolute maximums. So that sort of thing. Saddle points in a calc 1 sort of situation would look like x cubed. So there are places where the derivative is 0. That is, the tangent line is 0. So if you have your x cubed function like this, and we talk about at this point 0 here, if you were to draw a tangent line, the slope is 0, right? So our derivative is 0 there. So it would be a critical point in the calc 1 sense. And yet when I look at this critical point is not a minimum and it's not a maximum. Because if I go just a little bit to the right, I can get bigger values. So it's not a maximum, right? Because there's bigger values close by. And it's not a minimum because if I go to the left, I get smaller values. So back in calculus 1, I just call these boring critical points, right? That they're just nothing special. And so it's the same thing for here in calculus 3. Let me see if I can quickly draw a saddle with something like that. So I'm trying my best to draw like a Pringles chip sort of deal, right? Or the classic saddle that you would ride a horse with. So my claim is at 0, 0, that this is neither a minimum nor a maximum. It is a critical point in the like we calculated out and we see that 0, 0 is a critical point. However, if you were to kind of ride this parabola here, it looks like it's a minimum. And yet, if you were to ride this parabola here, this other cross section, it's going to look like it's a maximum, right? So there are smaller values nearby, and there are bigger values nearby. And so that's why it's not a minimum, because right, there are smaller values nearby. You can get smaller than that close by. And it's not a maximum, because you can get bigger values than that. It's just more difficult to visualize because it's 3 dimensions. Good. Yep. Does this apply to all hyperbolic paraboloids? First of all, we have to realize that this entire setup here is for situations where we have z equals a function of x's and y's, right? You could play this game about switching switching variables and stuff like this. But all of this is done for explicit functions, z equals something, right? And so you don't have these hyperbolic paraboloids that are kind of in these other directions. And then, yes, they will all have a saddle point. That is a true statement. All right. Well, then, let's try a harder problem then. So find and identify all local maxima, minima, and saddle points for this function. So chose some slightly different wording here, but again, the heart of the question is the same. We need to find and we need to identify or classify, right? What are those critical points? Are they minimums? Are they maximums? What are they, right? So I would like to give you maybe 60 seconds or so. I'm not expecting you to get finished by any means, but I'd like you to get to the first kind of roadblock or the first little, problem point with this to see that it's harder, right? So again, 60 seconds or so, work on your own for a minute and just kind of get to that first place where it starts to get difficult. All right, so I think many of you have found it, that this system of equations is considerably harder to solve than maybe our last system of equations, right? The last ones were quite easy. Again, we found that there was no way to make this undefined, and so our only hope is if both of them was equal to 0, and then we could just solve very quickly, and we got a point, right? And there was only one answer to this. In this situation here, again, we can look at this and say there's really no way to make this undefined, either one of these, right? There's no square roots, there's no division, there's no natural logs or anything like this. And so really our only hope is if both our x derivative is equal to 0 and our y derivative is equal to 0. And so we have this system of equations that we need to try to solve, right? What are the possible x, y values that would make these things true? And so there's several different ways that we can go about this. I'm going to go ahead and do maybe a substitution method for system of equations. So I'm going to go ahead and maybe rearrange this one here, and I'm going to get 3y is equal to negative 3x squared. I can divide by 3 on both sides, and maybe the simplest that I can make this look is that y should be equal to negative x squared. Now, once I have that, I can go ahead and plug it into my second one. And so that's going to say, what? 3x plus 3. And instead of that y there, I'm going to go ahead and substitute in negative x squared. So y squared, so again, there's kind of two squareds going on here. So again, let's try to simplify this a little bit. So this is going to be, what? Negative x squared times negative x squared is going to be positive x to the 4th. And now, well, let me show you maybe the slightly wrong way to do this. So I would go ahead, and if I wanted to do this slightly wrong, I may rearrange this a bit. And then, I can divide by an x and a 3. So I would have something like this. Then I could divide by that negative. And so x would be equal to negative 1. Remember, square roots and fourth roots and all that sort of stuff, they really don't like negatives, but odd roots are perfectly fine with it, right? Negative 1 times negative 1 times negative 1, aka negative 1 cubed, is equal to negative 1, right? And so the cube root of negative 1 is a perfectly fine number, and you can plug it into your calculator too, right? Your calculator will tell you that the cube root of negative 1 is negative 1. All right, so this is an answer for sure, but it's not the only answer. It turned out I messed up someplace. Can anyone tell me maybe what I did wrong? Yeah. I lost a solution when I divided both sides by x. That's absolutely true. So when you divide by x, you are assuming that x is not 0, right? Otherwise, you've divided by 0, and you've kind of ruined things, right? And so another solution happens when x is equal to 0. So dividing by a variable is always a little bit, you have to be careful because you may accidentally be dividing by 0, even though it doesn't look like it, right? And in which case you lose a solution, right? But of course, you can go back even as early as here, right? And if you plug in x equals 0, it's a true statement, right? So that should be a solution that comes out. So typically what I do that's a little bit safer, rather than kind of moving around and dividing like this, is that it's always safer to kind of factor polynomials. So if I was looking at this line up here, what I would do personally is factor out the GCF, right? Greatest common factor, and that would be 3x. And then I'd be left with 1 plus x cubed after I did that factoring. So now we have a product of two things that must be 0. So that means that either 3x is equal to 0, which gives us our solution that we missed, or 1 plus x cubed must be equal to 0, which turns out to be exactly x is equal to -1. So in this method, we get both solutions. So with that, we now have both of our critical points. Well, we have the x values for their critical points. I suppose we also need the y's, right? So if I was to go ahead and maybe back into up here, this y equals -x squared. And if I was to plug in 0 into that, I would get y is equal to 0. And if I was to plug in -1 into that, right, I would have -1 squared. That would be +1, but then I need to make that negative, right? So that would be -1. So my two critical points, 0, 0, and -1, -1, are the critical points. I find that it's also sometimes useful to solve these kind of graphically. And so I want to illustrate that really quick before we move on. So let me just look at this line of reasoning right here. This all had to do with me trying to make my x derivative equal to 0. So all of this meant that really I need to be on this curve y is equal to -x squared. So if I was to draw this out, because again, I want to do it graphically, all the places where my derivative, my x derivative is equal to 0 are along this parabola right here. Those are all the places where my x derivative is 0. We could play a similar sort of game with my y derivative, right? If I was to try to isolate and figure out where are the places where my y derivative was equal to 0. Remember, I took my y derivative, set that equal to 0. And if I rearrange this a little bit, I could get what x is equal to -y squared. So again, divide by the 3, subtract the y squared from both sides. And this again is going to be a parabola. It's a little bit more of an annoying parabola because it's an x equals parabola. And so just like we did in 12.6 when we were graphing, parabolas and ellipses and hyperbolas and whatnot, you're certainly allowed to use the point plotting method for these. But it turns out that this is going to be a parabola that's opening towards the left direction. The y equals parabolas open up or down, depending on if you have a positive or a negative for the leading coefficient. And then the x equals parabolas open to the left or the right. And again, we see that negative. That means it's going to open towards the negative x's, the left. So again, this is all the places where my y derivative is equal to 0. And we have all the places where my x derivative is equal to 0. And remember, I want both to be true. I'm looking for places, therefore, that these curves intersect with one another. So it looks like there's an intersection here at the origin. That is a place where both my x derivative is 0 and y derivative is 0. And there's an intersection down here, which turns out to be -1, -1. Again, a place where both of these things are true. My x derivative and y derivative are both 0. So this is a nice way to also kind of visualize and make sure that we have all of the points too. All right, so step one complete. We have now found all of our critical points. So step two is going to be, well, classifying these or identifying them. Are they minimums, maximums? What are they? So just as before, now we need to take our second order partial derivatives, right? So I need my f sub xx, f sub xy, f sub yy. I'm going to cheat using technology a little bit just so I don't have to keep on scrolling back and forth and back and forth. And I'm just going to put a copy of my first partial derivatives right here. All right, so looking at my f sub x, taking another derivative with respect to x. So I'm going to have 6x. Looking at still my x partial derivative here, but now I want to take a derivative with respect to y. That's going to be 3. And then finally, I need two derivatives both with respect to y. So I'm going to start with my first order partial derivative here and take another derivative with respect to y. So that's going to give me 6y. So this d value is going to be 6x times 6y minus 3 squared. There it is, fully simplified. So for the more complicated functions out there, like this one, you can notice that the d, I mean, you have to plug in your specific point. It may give you different values depending on what point you plug in, right? So in our first case, which was a little bit on the nice side, right? The d, you didn't have to plug in the specific point because there was only one critical point. But here you can see we haven't gotten rid of all of our variables completely, and it does matter, right, which we plug in. So let's say at the critical point 0, 0, and let's start classifying that. So at 0, 0, our d value, so plugging in both 0 for x and 0 for y, we're going to get that this is equal to -9. Just like before, I would say that this is less than 0, because that's the main qualifier that we're looking for to identify or classify our critical point. So 0, 0 is a saddle point. So that's one of them. The other one is at -1, -1. d of -1, -1 is going to be equal to 36 minus 9, so 27, and that's greater than 0. Remember, when you have this determinant is greater than 0, we're in calculus 1 world. So in calculus 1 world, we need to now figure out, looking at our second derivative. So let's go, our second derivative, both with respect to x, is 6x. So let's just say f sub xx is equal to -6, because again, we need to plug in our specific values. -1 for x, -1 for y. There doesn't happen to be any y's currently. This right here is less than 0, which means we are concave down. So when you're concave down, right, being stretched downward, that means that you have a maximum. I know if you're going too fast with these, you see -6 and you say -6 is a small number, it's a minimum, right? Something like this. So be kind of careful with that, right? It's that -6 has to do with the concavity. It's not the value itself. So the concavity is negative, which means that you have, it's bending downward, which means that you have to have a maximum. All right, so I have found and I have classified both of our critical points. So you can see that these things do get harder when you kind of get more complicated functions, right? The system of equations is more difficult, and then everything's kind of just stepped up a little bit. Question, yeah. Great question. So yeah, in the rule that we have up here, And this is, again, kind of comes from the textbook and whatnot, right? That we have the second derivative, both with respect to x, is somehow more important than the partial derivatives with respect to y, right? And the question is, why is x, I mean, it happens to be just the first variable on the list, but why does that make it so much more important than your two partial derivatives with respect to y? And the answer is that it doesn't. That you could have written this, the same textbook essentially, using two derivatives both with respect to y here. So you could use either one of them, and they both work. So I mean, you can follow throughout, in all of your webworks and whatnot, and kind of verify that that's true in this case, right? If we used our partial derivatives both with respect to y, again, we would get -6. -6 is negative, less than 0, and so it would still be a maximum. So nothing's really special about derivatives both with respect to x. I mean, they do have to be with respect to the same variable. So it's either both x or both y. You can't do the mixing. But yeah, either x or y would work perfectly fine. All right, good. Any other questions? Yeah.
We know like which points to, like I know for this graph is really nice and whatnot, but what's stopping us from saying like -1x and y0, like for like more complicated problem?
So, I mean, ultimately at the end of the day, and let me repeat the question just to make sure everyone heard it, and for the video and whatnot, is if you took some combination of these, right? So if you had x being -1, but then y being 0, right? Why doesn't that combination work, or how would we be able to tell, right? Is kind of what I heard there. And so any of these you should be able to plug back into our original equation and verify that both your x and your y derivative are equal to 0, right? And if they're not, then that means that you've made a mistake somewhere, right? And so that's a great double check to do, especially for more complicated problems, right? When it gets more complicated, and if you're not sure if maybe you've mixed something up and they shouldn't have, this exact, like you said, maybe you say, well, I have these bits right here, but maybe x could be 0 and y could be -1, right? Can I do that combination? Well, when you go back here and we try to plug these things in, x equals 0, y is equal to -1, we would have, what, 0 minus 3. So you could see really fast that this actually doesn't give you a critical point, because the x partial derivative isn't equal to 0, let alone it turns out the y partial derivative also wouldn't be equal to 0. So you wouldn't get a critical point. But yeah, this is a quick double check. Yeah. One more question, and then we can move on to the last problem of the day. Yeah. Are there three-dimensional inflection points? Yes. But in order to visualize them, you have to be able to view in 4D, right? So. Oh, maybe I misunderstood your question. Sorry, inflection points, three-dimensional. So if you have x's and y's, inflection points like that. Sorry, I was thinking about, I replaced inflection with saddle points or something like this. So that, so yeah, I mean, mathematically you can define these things. This is where your concavity would change, and you would probably first restrict down to specific variables. So you could do this where the inflection point is in the x direction versus where the inflection point is in the y direction. So how these things change. And then, yeah, what do inflection points look like if you want like both of these things to be true? I'd have to think more about that. It's a good question. All right, last question, and then we have a problem to do.
Like explicit functions?
Yes. This is all for explicit functions. You need z equals a function of x and y to do any of this. All right, so I would like to give a new method for finding the shortest distance between a couple of objects. I would like to start off by doing a problem that we could have had in like 12.5 or so. And so there are other methods in order to solve this particular one here. But the method that I teach here is going to be applicable for many more surfaces than just a point and a plane, right? So I mean, suppose you had a point and elliptical paraboloid, then the method from 12.5 doesn't work, right? Or you had a point and some interesting ellipsoid or something like this, right? Or just some other interesting surface. And so you can find now shortest distance between a couple of objects, even if it's not a point in a plane. But we'll start off with the easiest scenario here. So ultimately, at the end of the day, what I'm trying to minimize, right, is distance. I would like to minimize a distance function here. And so let's go back to our 12.1 days. And I am in 3D space. So we're going to have our distance formula was given to us like this. And so this is the thing, oh, I forgot my squared there. This is the thing that I would like to minimize. Now I'm in trouble if we just left it like this, because I see 1, 2, 3, 4, 5, 6 variables. And I'm now better at minimize and maximize things with 2 variables, x's and y's, but 6 variables is a whole nother beast, right? So hopefully I can plug in some specific things. Well, one thing that I see here is that one of our points is fixed, right? So let's go ahead and say that this is my x1, y1, z1. And I can plug in those specific values. So I'm going to get the distance now, not from 2 random points in space, but right now we have 1 random point in space, and the other point is going to be fixed. 0 and z2 minus 2. All right, so now I'm down to 3 variables. I'm feeling a little bit better, but still I'm only really good at minimizing and maximizing right now with 2 variables, x's and y's. So the last thing that I can use is that our other point, my x2, y2, z2, is not a random point in space, but it needs to be on this plane. So that means that if I let x2 be just regular old x, and if I let y2 be regular old y, then z2, if I want it to be on the plane here, I can go ahead and rearrange this and get a z equals function. And that will guarantee that I'm on this plane. If I chose other z values, right, I may not be on the plane. So now with this, I'm going to get a distance. And again, I'm going to switch to my variable x and y. And instead of z here, I'm going to put 4 minus x minus 2y, because that's going to force us to be on the plane. So now this distance formula here is the distance formula between the point 1, 0, 2, right? I plugged that in. And because I've swapped out not just any old random z, it's the z that's equal to, you know, this plane equation here, this 4 minus x minus 2y, we now have a function that models the situation. That gives us distance between our point and our plane. And so this is the thing that I would like to minimize, right? I'd like to find our minimum distance here. And so, well, this is the point where I could go ahead and start taking partial derivatives and figuring out when these things are equal to 0. And that would work perfectly fine, but it is fairly complicated with this big function here, with the square root and all that sort of stuff. So I would like to give us a bit of a trick here that'll make this a bit easier. At the heart of this, we have the square root of a bunch of stuff. I'm going to do square root of star. You can do square root of u if you want a more conventional variable here. But square roots look like this. They're nice increasing functions. It's the positive square root, so at worst case, they give out 0. And then after that, the farther to the right you go, the larger the value gets. So I'd like to give us this idea, or I'll even call it a theorem. And that is to minimize the square root of some stuff. I'll use the square root of f here because it could be any old function. You can simply minimize f. I guess I should include on here that the function that you plug in needs to be positive, right? If you are able to plug in any negatives into that, that would be a problem. So here, we'll add in additional hypotheses for positive functions. So this is saying that if I can minimize what I'm inputting into my square root, right? If I can get as far to the left as possible versus other points, farther to the right, they will give smaller outputs than if I was to plug in something, a larger f. And this is true for all increasing functions, right? So if you have an increasing function, plug in something as far to the left as possible, plug in as the smallest value you can, right? And that will guarantee that your output is as small as possible. Because if you plugged in larger values, right, an increasing function would get bigger. And that's what happens with the square root here. So that's why this will work. And so all this to say, I would like to define f to be just what's inside of my square root. And I'm going to try to minimize this. And if I can minimize this, again, this is the thing that I'm plugging into my square root, that will end up minimizing this distance. And we can also see that because I'm taking a bunch of things and squaring them, adding them together, that it's certainly going to be positive. So I don't have to worry about really this hypothesis in this particular case. And this is going to be a lot easier to take the derivative of. Any questions before I go on to the next step? Okay, you'll have a Weber problem that's like this. I think it's a point and a cone in the Weber problem, and it gives the same hint. So if you don't use this hint, right, where you can kind of ignore the square root temporarily, right, it becomes much harder. So I would invite you to remember this problem when you're doing this one on Weber. All right, so let's go ahead and start taking some partial derivatives. So derivative with respect to x, we're going to have 2x minus 1 times the derivative of the inside, that's just 1. Plus 2 times 2 minus x minus 2y times the derivative of the inside, again, with respect to x here. So we get -1. Now, derivative with respect to y, we're going to have 2y plus, and again, we're doing a power rule here. That's why the 2 comes down, leave the inside alone, then multiply by the derivative of the inside. And again, this is a derivative with respect to y. And so the derivative of these other pieces that don't have y's are just 0. And the derivative of -2y gives us this -2. There's no way to make these undefined. And so our only hope is that maybe if both of them are equal to 0. So let's go ahead and start simplifying this a little bit and trying to figure out when this would be equal to 0. So I'm going to have 2x minus 2. And then I'm going to try to distribute this -1 and this 2 to each piece. So -2 times 2 would be -4, then plus 2x, and then plus 4y. So I'm going to have 4x plus 4y minus 6. If you see me make any mistakes, please speak up sooner rather than later, because there's just a lot of little places where you could make a small mistake. All right, next up, let's simplify the next one. This one I need to multiply by -2 and 4, and I'm going to distribute these to both, all three pieces here. So -4 times 2 would be -8. -4 times -x would be plus 4x. And -4 times -2y is going to be plus 8y. So this is going to be 4x plus 10y minus 8. All right, so if I want f sub x to be equal to 0, I need it to satisfy this line equation. Oops, that's not a 6. And if I want f sub y to equal 0, I need it to satisfy this. Now we have our system of equations that we need to solve for x and for y. This is nicely set up. They both have 4x here. And so instead of using the substitution method, I would probably use linear combinations and just subtract one from the other. So when I do that, I'm going to have what? 4x minus 4x, that's 0. 4y minus 10y, that's negative 6y. Negative 6 minus a negative 8, so that's going to be plus 8, so it's going to be plus 2. And so we're going to have negative 6y is equal to negative 2, or y is equal to 1/3. Once we have that, we can plug in our equation into either one of these. And that's going to give us our x value. So yeah, I see that I am out of time. So maybe this is going to be a good place to end. Well, not a good place to end, but an appropriate place to end. I will continue writing this out, and I'll post the full solution on D12, hopefully by 4 o'clock today. But this is, I think we've done the majority of the hard stuff. So I think that you could also solve this problem on your own from here on out. So please try that. And then, you can peek at the solutions on D12 and see if you got it right. All right. Well, thank you so much. Good luck on the quiz tomorrow. I'll stick around if you have any one-on-one questions. Otherwise, see you Friday. We have another day of this. We need to talk about absolute mins and maximums. So that's next time.